Okay, with the next theorem, okay, we have entitled linear transformation given by a matrix. And if we let A be an m by n matrix, where we have the function t is going to be defined by the linear transformation of the vector v is equal to the matrix A times that vector. And that is going to be a linear transformation going from the vector space Rn into the vector space Rm. And in order to conform to matrix multiplication with an m by n matrix, n by 1 matrices represent the vectors in Rn, and m by 1 matrices represent the vectors in Rm. And for what we have regarding a linear transformation given by a matrix, say we have in the case of this problem where we have a given matrix A is equal to a 2 by 2 matrix consisting of 0, -1 and in the top row and -1, 0 in the bottom row. And we're looking at defining the linear transformation t as we go from Rn to Rm by, once again, the formula whereupon we have the linear transformation of the vector v is equal to the coefficient matrix A times the vector v. And it says to find the dimensions of Rn and Rm. Okay, so for this matrix A, m is going to be the number of rows, which we're going to have at 2. N will be the number of columns, okay, which is going to be also at 2. And for what we have for the linear transformation, the vector v equal to the coefficient matrix A times v, that is going to be a linear transformation from Rn to Rm. And so since the size of A is going to be 2 by 2, it's going to define a linear transformation going from R2 to R2. So here we have the linear transformation going from R2 to R2. And so for what we have in terms of the layout, okay, so we have for A times V, okay, so we have the matrix A, 0, -1, -1, 0, and corresponding to R2, we have for that vector space, okay, we have a 2 by 1 array, so you have V sub 1, V sub 2, and for the output, okay, we have U sub 1, U sub 2, and both of these are in R2. And for what we have in the case of what we have for this exercise, we have a 2 by 5 matrix where we have in the top row for A, we have -1, 2, 1, 3, and 4. Bottom row we have 0, 0, 2, -1, and 0. So for this matrix A, m is going to be at 2, and the number of columns is going to be equal to 5. And once again, for the transformation of V equal to A times V, again, we're looking at a linear transformation from Rn to Rm. Okay, so N is going to be at 5, M is going to be at 2. So for the size of a coefficient matrix as a 2 by 5 array, this case is going to be where we have defining a linear transformation going from R5 to R2. So just looking at what we have here, so we have, again, the linear transformation defined going from R5 to R2, and just kind of giving a bit of a bird's eye view. So for what we have in the product of, or the setup in the determination of the product between the coefficient matrix and the vector v, and in terms of how this is going to be established, so we have, again, for the matrix A, we have a 2 by 5 array, and for what we have in the vector v, okay, we have a 5 by 1 arrangement. And going back to the old rule, okay, we have like a 2 by 5 by a 5 by 1, okay, and the 5s match, and you have the number of rows in the first matrix times the number of columns in the second matrix. Okay, you had the dimensions to be 2 by 1, which would be the dimensions of the output matrix. So this is what we have in this case. They have R5 represented by, again, the 5 by 1 array of the subscripted values v, and we have R2, okay, in reference or symbolized by what we have in the output with our U sub 1 and U sub 2 for the elements.